Now we discuss for the perturbation in the case for degenerated case, and degenerate perturbation theory. In previous lecture, then we talk about the non-degenerated perturbation case. For example, in the first order perturbation, case, energy eigenvalue of the can be write down as zeroth order, and the first order energy correction is the ground state Hamiltonian, perturbed Hamiltonian, and zero. And in this case, and the energy eigenstate n0, it is a non-perturbed eigenstate, and the perturbed state is that summation for m, but it is different with n. Here, the numerator in the m0, h prime, n0. n0 and state m0, and the energy difference en0 minus em0, because in the here, because the numerator should not be 0, so en0 should not be equal to en0. Yeah. So it is a non-degenerate case. Surely it is a non-degenerate case. And in the second order equation, or the higher order equation, also can be write down as that in the second order. For example, in the second order perturbation, energy eigenstate for second order is that second order perturbation is the summation for m, but different with n, and it is high order. It is n0, h prime, m0, and absolute value n square, and en0 minus em0 here. So in this case, and the numerator should not be equal to 0. So here, the energy eigenstate and second energy perturbation is like this, and the second order energy state, it is that energy state second order. For example, it is a second order. Let me denote as only the second order. Then in this case, for the summation with m but different with n, and the summation with l but different with n, then here the state is m0, h prime, l0, and l0, h prime, n0 over en0 minus em0, en0 minus el0. And so another correction is that minus summation m should not be equal to m, and also m0 h prime, n0, and n0 h prime, n0 in this case, and l equal to n case. So in this case, en0 minus em0 square. It is a second order energy state. Here, because in this case, it is important that it is the non-degenerated case, and the energy eigenvalue should not be equal to with each other for the n state and m state. But it is very special case. In the degenerated case, it's a special, but what's the case in the degenerated case? For example, in the case of the energy, En and En equal to with each other, then here the denominator it becomes a zero, so it makes that infinity. So it is non-reasonable. So here to consider for this, and let's assume that n equal 2 and n equal 3 states are degenerate. With the same energy, E20, let's assume that. Then, in this case, and the first order perturbation equation is that H0 minus En0, and first one is that En1 minus H prime N0. It is a first order perturbation equation. Here H0 is diagonalized, so diagonalized and well-defined the energy eigenvalue. So E10 and E20 and E30 and E40 like this, and but it is diagonalized, and also like this. It is diagonalized because it is n equal 2 and n equal 3 states are degenerate. So, and we should note that n equal 2 and n equal 3 states are degenerate. So we can write down as H0 minus E20. Then it is one that E10 minus E20. In the second thing, here E20 minus E20 equal to 0, and the E30 also equal to with each other, so it is also 0. Yeah, so we call it is a 0, 0. So 0, 0, and E40 minus E20. Other things are 0, all of the 0. Here we know that it is 0, 0, 0, 0, this matrix. And here it is all these terms equal to 0. It is also diagonalized, and also eigenvalue H0 minus E20 becomes a 0 in the degenerated case. In the right-hand side of this one, and for example, this right-hand side, and let's denote that E21 minus H prime, then basically E21 also diagonalized, and E21 minus H11 prime minus H12 prime minus H13 prime minus H14 prime like this, and also minus H21 prime in this row, E21 minus H22 prime, and also minus H23 prime minus H24 prime like this, and also minus H31 prime, here minus H32 prime, E21 minus H33 prime, also minus H34 prime like this, minus H41 prime, minus H42 prime, and the minus H43 prime, here E21 minus H44 prime like this, and it is matrix. Because we should note that it is a 0, so this term corresponds to this matrix and inner matrix. So in this inner matrix correspond to the 0. So, and also we can think that and also in the first order, second state can be write down in arbitrarily in the C21 first order, C22 first order, C23 first order, like the C24 first order, like this. And also in third state, and the first order third state also can be write down C31 first state, C32 first state, and the C33 first state, C34 first state, like this, and it is third state. As you know, in the second for ground non-perturbed state is that 0, 1, 0, 0, and like this. And also third one, case 0 in non-perturbed case is that 0, 0, 1, 0, and like this. Here basically we should compare with each other, and because it is very important that this one, let's keep in mind this equation. Then if we found that the energy correction to the state here, for example, in the here, if we find the energy correction to the state with the E20 in the state with E20 case, and how we do know that whether to use the states in here E20 or 30 case. Then for example, and we should make that this one anyway, and here let's denote that new state for E20 state as a new state, and also can be anyway, it is a linear combination of the 0, alpha, beta, 0, and like this. And it is alpha means that here this term, and beta is this term. And so this new state is a linear combination of 20 state and 30 state, because it is a new state. So we should keep in mind that in the left hand side the Hamiltonian equation is the H0 minus En0, and first order energy state is that basically in the matrix, the matrix is like this. And also in first order, and the first order is that in general, first order energy state is here, because we only consider for the n equal to I'm sorry, needs to be this kind of matrix. It is n equal to state. Then here we calculate, it is this first rule is that E10 minus E20 and the C21 first state, and so here second and third is equal to 0, and here E40 minus E20 and C24 first order, And also, let's keep in mind that it is a zero case, correspond to the zero case. It is the left-hand side. And how about the right-hand side? Right-hand side is that En first order H prime and N0. And the E1 minus first prime is here. Here, and also new state for second order is that like this. It is a linear combination state. Here we can write down as the zero, alpha, beta, zero, and like this. Then we can calculate this one in the 0 minus H12 alpha minus H13 prime beta. Here 0 and E2 first order minus H22 prime alpha minus H23 prime beta, and also minus H32 prime plus E2 first order minus H33 prime beta, and also minus H42 prime alpha minus H43 prime beta, like this. Then because in this term, this red block corresponds to this red block here. So this one, from the equation of the right hand side, and here it is the left hand side, should be equal with each other. So it is second or third state. Second or third state correspond to 0. So here we can think that this term should be 0. It means that here when we make this one as a matrix, then here we can say that H22 prime, H23 prime, H32 prime, H33 prime, and alpha, beta, and here E2 first order alpha, beta. It is energy equation for degenerate energy. Here it is energy equation for degenerated energy. So here we assume that it is degenerated energy is n equal 2 and n equal 3 is a degenerated case. So we can make that this kind of matrix. Here we know that it should be diagonalized from this equation, and from the diagonalization and the determinant of the E2 first order minus H22 prime E2 first order minus H33 prime minus H23 prime minus H32 prime should be diagonalized. So it is E2 first H22 prime and E2 first order minus H33 prime minus H23 prime H32 prime. should be 0. Then we can calculate, and here e to first order square minus h22 prime plus h33 prime, and e to first order plus h22 prime h33 prime minus h23 prime h32 prime should be 0. And also from the here it is a second order equation, so we can obtain the two solutions. So let the two solution, one solution 2a first order, the other solution 2b in the first order. Then here e to a is that the ground state energy and also unperturbed energy plus, and the degenerated 2a first order, and e to b equal to e to 0 plus e to b first order. Here, therefore, it means that when the energy is degenerated and diagonalized perturbation Hamiltonian, and here important thing is that here diagonalize the perturbation Hamiltonian, in the degenerate subspace. It is very important. We should remember here it is diagonalized perturbed Hamiltonian. Basically, here basic equation is like this. Basic equation like this, and also zeroth order Hamiltonian, first order state, first order energy, and zeroth order state. Then from this matrix, and if you assume that second order and third order, second state and third state is energetically degenerate, then it makes that 2x2 submatrix. Here is E20, E30. Then it makes that 2x2 matrix. And in this case, and from this equation, and left hand side and right hand side make that this kind of matrix, so it can be 0. So here, in other words, it is a diagonalization. It's same with the diagonalization of the matrix of Hamiltonian. So it is perturbed Hamiltonian to the 2, 2 and 3, 3, and the 2, 3 and 3, 2. It is if here's n equal 2 and n equal 3 energy state is diagonalized, and also from this diagonalization and can be write down as it is a determinant eigenvalue can make that energy eigenvalue state. So how about in this case, in the second state and third state are energetically identical, but in other cases, for example, n equal 3, n equal 5, and not sequential, but with a different energy eigenstate, then in this case, and the matrix permutation, we can think about the matrix permutation. So then in this case, and also generally, and n equal 2, n equal 3, and very close with each other, and the nearest energy state should be degenerate and not far from the state. For example, n equal 2 and n equal 5, it is not degenerate. And for example, in general case, and n equal 2 and n equal 3, whether n equal 2 or n equal 1, and the nearest energy eigenstate can be degenerate, but different, far from the original state. Degeneracy is not imaginable. So, and we can make that 2x2 whether n by n matrix, and solve the diagonalize the Hamiltonian matrix can make that degenerated perturbation we can solve the degenerated perturbation theory. Here we let's consider for the examples, and here let me see the examples. Let me see the example. An electron is bound to move on the surface of the sphere. Bound electron at the surface of a sphere. Here, find the energy correction by perturbing magnetic field. Here is perturbed magnetic field. B prime is B1x, x direction. And let's solve this one. And in this Hamiltonian equation of a sphere, and can be write down as from the spherical coordinate, and from the spherical coordinate, the Schrödinger equation can be written like this: and the 2 mu r0 square h bar square 1 over sine theta and partial theta, and sine theta partial theta plus 1 over sine square theta and partial square and partial phi square and psi, and potential VR0 psi equal to E sphere psi. It is the Schrödinger equation in the spherical coordinate. Here we know that we denote that the spherical harmonics and the theta phi can be written like this: theta component and phi component can be separable, and also moment of inertia I equal mu0 r0 square. It is moment of inertia of classical particle. So we already know that it is L square is like minus h bar square 1 over sine theta partial theta and sine theta partial theta plus 1 over sine square theta partial phi square. It is operator of the L square. So there is an energy eigenvalue equation: L square over 2I y theta phi is that energy sphere y theta phi. Here, and we already know that Lm state, it is that the y Lm theta phi, also L state h bar square over 2I and L plus 1. And here we apply the Hamiltonian, perturbed Hamiltonian, h prime equal to minus mu L dot b. It is perturbed Hamiltonian. Perturbed Hamiltonian by magnetic field B prime. Here electromagnetic moment mu L is then minus E over 2 MEL. It is electromagnetic moment. Then the Hamiltonian can be write down E over 2 ME and L dot B prime. Then it is like that because magnetic field along the x direction, so E over 2 ME and the LX B1. Then in other words, omega 1 LX here, omega 1 is that EB1 over 2 ME. It is a Rameau frequency. Here, and for L equal to 0 and E 0 state, E0 state with the unperturbed state, ground state of unperturbed state is 0, and then L equal to 1, and the E1 0 is that 2i h bar square, and because it is L and L plus 1, so it is multiply 2, so it is h bar square over I. So we already know that for L equal to 0 case, there are magnetic quantum number should be 0. And L equal to 1 case, orbital quantum number 1 case, and magnetic quantum number, there are 3 degenerated case, 1, 0, minus 1. Basically, it is a degenerated case. So it is a triply degenerated. Hamiltonian is that here L equal to 0 and it is energy 0, and L equal to 1 case, and the energy is that h bar square of I, and also 0 state L equal to 1, m equal to 1 case, L equal to 1 and m equal to 0 case, it is that h bar square of I, and also h bar square of I, then it is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, like this matrix. So it is triply degenerated. It is a triply degenerated, so it is a 3 by, we can find a 3 by 3 subspace matrix. It is a threefold degenerated case. And here, here we know that Lx is that h bar over square root 2, and the matrix is that 0, 1, 0, 1, 0, 1, 0, 1, 0. It is Lx. Then this Hamiltonian H prime. Hamiltonian H prime is that here we know that omega 1 Lx. Omega 1 Lx. So it is omega 1 Lx, so h bar omega 1 0, 1, 0, 1, this matrix subspace. Then, for example, this Hamiltonian H prime can be write down L prime, M prime, L, M case, and here 0, 0, and the 1, 1 case, 1, 0 case, 1 minus 1 case, it is L and M, it is a 0, 0 case, L equal to 1 case, there are 3 case, 1, 1, 0, 1 minus 1, 3 possibilities. So in this 0 case also all of the term 0, and the 0 case also 0, and also matrix is that here the matrix H prime, there are 3 by 3 matrix. It is H prime means that omega 1 Lx, omega 1 Lx matrix. So H prime matrix is that 0, 0, 0, 0, 0, 0, 0, and also here, and here we should find that 3 by 3 matrix should be here, because Lx here is that the degenerate L equal to 1 case. So when you think about it, and here 0, h bar omega 1 over square root 2, 0, h bar omega 1 square root 2, 0, h bar omega 1 square root 2, 0, h bar omega 1 over square root 2, 0, like this. So it is a subspace. Matrix subspace is a 3 by 3 matrix. Here H prime for the L equal to 1 case. L equal to 1 case. So, and we should to analyze the energy equation, and we should diagonalize this perturbed Hamiltonian. So, and the diagonalization of this perturbed Hamiltonian, and also minus lambda, and h bar omega 1 over square root 2, 0, and h bar omega 1 over square root 2, and h bar omega 1 over square root 2, h bar omega 1 over square root 2, 0, and the determinant. So this determinant can be written down minus lambda cube plus, and the lambda cube, and here 0, 0, 0, here runs lambda 1, the first order lambda and square, and the first order lambda and the second order, and also lambda in h bar over 1 square root 2 square multi time 2. So it is write down minus lambda, then lambda square minus h bar square omega 1 square equal to 0. So lambda 0 or plus minus h bar omega 1. It means that there is energy shift for the E1A first order equal to h bar omega 1, and E1B first order equal to 0, and also E1C first order equal to minus h bar omega 1. So when in this case, for the energy eigenstate for under the magnetic field B1 prime, then L equal 0 case, 0 case is 0. L mx, L equal to 0 and m 0. And first one, here first n equal 2, n equal, here n equal 1, the unit is h bar square over 2i, and for 2 case, then L equal to 1. There are 3 degenerate like this, L equal to 1, 1, 1, 0, minus 1, and triply degenerated like this. So, and this basically, and we should keep in mind that if we think that there are energy eigenvalue degenerated for here in this case a triply degenerated case, then the matrix Hamiltonian, it is basically it is unperturbed Hamiltonian, but the perturbed Hamiltonian should be diagonalized, and we can know that the energy eigenvalue in the diagonalized state.